At the end of our last video, we made a promise. We were going to step back and do this right, and build a mid-power rocket the proper way. Simulation first, with real CAD software, real materials, and real motors. No shortcuts, no rushing, and no guessing. And then the rocket broke in half. Find out what happened in today's West-Tek Solutions video. If you've been following along, then you know that West-Tek's mid-power track record has been a little bit rough. 5 launches, 1 success. And that 1 success required a stranger's superglue and a little divine intervention in the Arizona desert. After the Yankee 1 disaster, where we built an underpowered, overweight rocket in a weekend and watched it flop back to Earth like a wet paper towel, we made a decision. We were going to design our next mid-power rocket the right way, from the ground up. That rocket is the Super-Strat. The same DNA as the Stratus, bigger ambitions, and for the first time in West-Tek history, a real engineering workflow. Before we touched any software, we laid out what we wanted this rocket to actually accomplish. We wanted to design it from start to finish in OpenRocket before touching anything. We wanted to move from Tinkercad to Fusion 360. We wanted to print in higher grade engineering filaments, specifically PETG carbon fiber. We also wanted to launch off a 1010 rail for the first time. We wanted to include positive motor retention, no more hoping the motor just stays put. We also wanted the rocket to be fully modular and threaded. And finally, we wanted to fly on composite motors. That last point is significant. Up until this point, every West-Tek rocket has flown on an Estes black powder motor, and composite propellant is a just totally different animal. So this launch was going to have a lot of firsts. We started in OpenRocket, which by now has become a core part of the West-Tek workflow. The first decision was body diameter. The Stratus flew on a 1.6-inch body. The Yankee 1 was 3 inches. We landed on 2.56 inches, right in between. For the fins, we went with a clipped delta design, borrowing a little from the Stratus and a little from the Yankee. The fin can would have interior threads at the top and bottom, allowing the motor mount to thread in from below and the lower body to stack on top. Every section from there, lower body, upper body, payload bay, nose cone, would thread together in one continuous stack. The idea was that any section could be removed, swapped, or reprinted without touching the rest of the rocket. After some back and forth in the sim, we arrived at a design that OpenRocket liked. 32 inches tall, projected mass around 400 grams, without a motor. Now we just had to actually build it. Every previous West-Tek rocket was designed in Tinkercad. It's fast, it's accessible, and it got us pretty far, but we'd outgrown it. For the Super-Strat, we committed to Fusion 360. I'm not going to sugarcoat the learning curve. Fusion 360 is a genuinely powerful piece of software, but stepping up from Tinkercad kind of felt like I was taking a calculus class having only taken addition. Fortunately, I found a fantastic tutorial by Lafayette Systems on YouTube, link in the description, that walked through designing a rocket in Fusion 360 from scratch, and I highly recommend it. Before long, we had STLs for the fin can, the motor mount, the body sections, the payload bay, and the nose cone. With the STLs in hand, I passed them to Bob. This project was also an opportunity to push into new materials, specifically PETG carbon fiber. PETG CF is a composite filament, PETG plastic reinforced with chopped carbon fiber strands. The result is stiffer, lighter, and more dimensionally stable than standard PETG, with a matte finish that, frankly, looks awesome. I'll be honest, I was a little worried about brittleness. Carbon fiber reinforced filaments can be less impact resistant than straight PETG, but with 2mm thick walls on the body tubes, the parts came out feeling rock solid. So yeah, it's fine. Once everything was printed, I updated the OpenRocket simulation with the actual measured weights. We came in almost exactly where the sim predicted, right around 400 grams without a motor. Then we ran the simulations. With the real weights loaded in, we tested a handful of motor configurations. On the F26FJ, the sim predicted around 1,147 feet. On the F50T, we were looking at 1,282 feet. The G78 was a different league entirely, a projected 1,884 feet. That's nearly 2,000 feet off a mid-power motor. We settled on the F50T and the G78 as our 2 target flights. The F50 would be our checkout flight. Confirm the airframe, confirm the recovery system, confirm the rail setup. If that all went well, then we'd step up to the G78. A few weeks later, the motors arrived. We had the rocket, we had the propellant, and we had the data. Now it's just time to find out if any of it actually mattered. We made our second trip out to the URRG on a Saturday in late March. It was a completely different scene from the last visit. The weather had turned and the field was packed with college rocketry teams who had driven hours to launch. Bob and I got to work. We filled out our flight card, prepped the rocket, and approached the rail. So new rocket, new motors, new rail, new ignition system. First time doing all of it at once. So needless to say, we were a little bit nervous.
West has a rocket called Super-Strat. It is an orange and gray rocket. First one in to the left. Well, on the right end, I guess. It's on an F-50 motor. It's their own design in 3D print. So, hope this works. Alright, ready? I'm flying. 5, 4, 3, 2, 1.
But it flew. It actually flew. After 2 Katos at URRG last time, watching the Super-Strat cleanly leave the rail and punch in the sky felt genuinely incredible. The rocket went on to deploy at Apogee, drift down, and landed somewhere in the cornfield. Well, all we had to do now was go find it. I made a mental note of where I saw the rocket come down, and I thought it was going to be easy enough. It was not easy enough. The field beyond the launch site was a cut-down cornfield, and after recent rain, the mud was something else. In places, it came halfway up to our calves, and after 10-15 minutes of slogging through, we still had nothing. I genuinely started to think that we lost the rocket, this rocket that we had spent weeks designing and printing, but then suddenly Bob found it. We ran over, pulled it out of the mud, and were genuinely thrilled for about 4 seconds. Then we noticed it. The rocket had separated at the threaded joint between the lower body and the fin can, snapped clean at the thread. Our best theory is that the interior threads create a small lip inside the body tube. Then when the injection charge fires, that lip catches the blast, and on this flight, it was enough force to break the weakest point of the airframe. We stared at the rocket, and then we stared at each other. Then we looked over to our car where we saw the G78 motor was sitting untouched. This rocket was already going to be retired after this project. The threaded design was teaching us things, mostly that we need to rethink it before our level 1 certification, and we were planning to move to a more conventional body tube and coupler design going forward anyways, which meant, what did we have to lose? We lined up the separated sections, soaked the joint in Gorilla Glue, clamped it together the best that we could, and let it cure. Look, it's not pretty, but we didn't need it to be pretty, we just needed it to hold together long enough for one more launch off the G78. When the glue set, we loaded the motor and walked back to the rail and got in line.
Is this a certified? Brenda?
No.
Okay, not a certified.
Brendan.
RB3. This is a G78. You ready?
Ready?
Guys, going 5, 4, 3, 2, 1.
If anything, it actually flew straighter than the first time. The G78 is noticeably more powerful. More noise, more smoke, faster off the rail, and it pushed the Super-Strat to somewhere around 2,400 feet. Nearly half a mile up on a 3D printed rocket we'd glued back together 40 minutes earlier. And then the rocket deployed its 18-inch parachute at 2,400 feet. And if you thought the first recovery was a hike, this one was a full expedition. The parachute caught the wind and just kept going and going and going. And we watched it drift off into what seemed like a different zip code. We searched for 25, maybe 30 minutes, mud, sun, more mud. I was ready to call it. Once again, Bob spotted the orange, the unmistakable happy shoot orange, flickering on a field on the other side of a river. A river. There was a deep river between us and our rocket. The river was too deep to cross, which meant one of us was going to have to run around to the other side of the river. I will not be sharing my pace data for that run. When I finally got to the other side of the river, there it was, in perfect condition, not a scratch on it.
Swim.
By the time we got to our car, we were muddy, sunburnt, exhausted, and grinning. Here's where West-Tek stands. 3 successes out of 7 mid-power flights, the 2 most powerful motors we've ever flown, the highest altitudes we've ever reached, and a workflow that actually produces results. Did we do everything right? I mean, mostly. The threaded design definitely has some flaws, and we should definitely look into chute releases and trackers going forward, but the Super-Strat proves something important. The new workflow works. Simulation first, design, proper CAD, better materials, it gets us further. It doesn't guarantee perfect flights, but it gives you a fighting chance. And for West-Tek, a fighting chance is all we need. The level 1 cert is still on the horizon. Next up, we'll be designing the Yankee 2, our first true level 1 certification rocket, built on everything we learned from the Stratus, the Yankee 1, and now the Super-Strat. We're not there yet, but we're closer than ever before.